With further ado, I'm going to introduce our distinguished keynote, Emily Lakdawalla. She's a science writer and space artist. She covers solar system exploration for outlets including SwRI, Telescope, and BBC Sky at Night, and is a frequent radio and TV guest explaining planets and mission. Her first book, The Design and Engineering of Curiosity, was published in 2018. Please give her a warm welcome.
Good morning, everyone, and thank you for the honor of actually filling up the room at 8:30 in the morning. It's not something I anticipated seeing, so thanks for showing up. So, hi, my name's Emily Lakdawalla, and I thought I'd begin this talk by explaining who am I and why it's reasonable for me to spend your time talking to you about 25 years of Mars discoveries. I put a couple of somewhat self-deprecating slides in at the beginning for all of these talks, but I think they'll actually look probably quite familiar to a lot of you. This is me with my 4th grade science project. I was always interested in science. I was inspired by Voyager to be interested in space. I had all the space Legos. I had the Transformers. I was such a nerd and a big science fan growing up. Didn't know if it was going to be space, dinosaurs, who knows what. I wanted to be one of those scientists that I saw on all of the public television programs that were pretty much my set of my parents when my parents weren't at home yet. I was a latchkey kid, like a lot of kids my age, and I would come home and watch PBS. David Attenborough and James Burke and Philip Morris and all kind of inspired me to be interested in not just science, but in explaining science to people, to helping people understand how we know what we know. And so I went to college to study some kind of science, and I fell into geology, which was kind of a black hole for history and art majors at Amherst College, where I went to, because geology is a very descriptive science. It's a very storytelling science, because you have very tiny amounts of data, and you really just have to write stories that make some kind of sense to fill in all of the gaps. And there's nobody who can tell you you're wrong, because there's not enough data. So you just have fun storytelling and drawing pictures and getting to wander around rural New England in the fall with the pretty fall color. So that was pretty great. I thought geology was awesome. Straight out of college, I became a middle school science teacher, explaining science to 10-year-olds, which 10-year-olds are, by the way, my absolute favorite age. They're old enough to have some capability of logic, but young enough to still respect authority, which was necessary when I was 21, and the same age as some of their siblings. So it was fun for a couple years. But then, and they were a very important couple of years in space science. Space science had been kind of in the doldrums for a long time, but 1997 was a really key year. That was the year that Pathfinder landed on Mars, and this little rover named Sojourner first put 6 wheels on soil on Mars. And not only that, but all of the pictures straight from Mars were going out to the public via this really cool new thing called the World Wide Web. And you could go and download these pictures, and they'd warn you about the file sizes. Look, that panorama at the top was 47K. It would take forever to get downloaded on your slow modem, but it was absolutely worth it for these brand new pictures from Mars. You know, JPL was so overwhelmed by the data volume being demanded by the public that they had mirrors at other websites. The Planetary Society mirrored them. Some high school in rural Oregon was a mirror for JPL. You could like pick one of these other mirrors in order to, if JPL was overwhelmed, you could find like one of these, the images on one of these other sites that were offering up a little bit of bandwidth for the photos. So this was pretty amazing. I mean, this wasn't, you know, high-res video, but man, you got to actually see this little robot just deploy and get onto the soil, drive around. It was just absolutely amazing. It reminded me of a little beagle kind of walking around and sniffing at the rocks and then going around other different places. It was fun. So that experience, seeing those images, made me think, you know, cock my head like a beagle and say, I wonder if you can do geology on other planets. And it turns out you can. So I went to graduate school, and I went to Brown, which at the time, there were people that were working on all kinds of amazing missions, like Galileo and Mars Global Surveyor and stuff. These images are some of the first pictures of Jupiter's moons that came back from Jupiter since the Voyager missions back in the 1980s. So this was amazing stuff happening at the time, and we were getting these great pictures of all of Jupiter's moons. Sorry, I'm just grabbing my water. And what you can see in the background of this photo, which is Brown University's Regional Planetary Image Facility, are these gigantic metal cases, and those contained 30 by 40-inch printouts of every image ever produced by NASA's planetary exploration program and also the Apollo program before that. So those cabinets actually contained lunar orbiter photos, which I don't know if any of you guys have ever spent much time thinking about how lunar orbiter got its photos, but it took film, it exposed film that then developed inside the spacecraft and then was scanned with an analog scanner, and the analog signal sent back to Earth, printed out and then assembled into these photographs. It was absolutely stunning. So when I was supposed to be working, I would mostly be going up and like just rifling through these cabinets and seeing all these amazing photos. And I got to work on Magellan, which was a mission that had recently ended. And I was studying geology on the surface of Venus, and you can see the two little black arrows in that photo are pointing at two ends on the photo of a very skinny little canal that you can see rolling across the surface. That's part of Baltus Vallis, which is an 1,800-kilometer long channel on Venus. Now, Venus is an incredibly volcanic place. That can only have been a volcanic channel, but think about that, 1,800 kilometers long. That is a very long distance. And still, nobody has a real good explanation for how you can have a channel running quite that long. You have to have some weird kind of lava that is very runny and doesn't freeze for a long time. But one thing that scientists mostly agree on is that liquids flow downhill. So you can use this thing as a marker for what was either level or downhill at the time that it formed. And so I was studying how the topography related to that channel. And the funky thing is that the channel does this now. So the geology has been doing interesting things since that channel first formed, and that was the subject of my study. But most of the time, like I said, I was just rifling through cabinets looking at other cool Magellan images. So I was also privileged to work with some of the very first data coming back from the Mars Orbiter Laser Altimeter that was sent to Mars with Mars Global Surveyor in 1997, although the data weren't really coming down in a form that we could use until 1999 because that spacecraft had to aerobrake for a long time in Mars orbit. Okay, so when I finished my master's degree at Brown, I had one very unhappy year as an environmental consultant before I found a job at the Planetary Society, where I got to teach people about space and write blogs and have adventures like testing UAVs on Devon Island at the Arctic Mars Research Station and see the spacecraft arrive from the European Space Agency, be in the press room when Phoenix landed on Mars, go visit giant dishes, all that kind of fun stuff. And that kind of culminated in writing my book about the design and engineering of Curiosity. And there is a sequel in the works. It's been somewhat delayed by the pandemic and other things happening, but it is still about 60% written, and at some point it will be 100% written. This was a book I had to write in order to be able to write the book I wanted to write, which is about the science of curiosity. But it turns out, as with a lot of things, but especially rovers, you really can't understand the science unless you understand how the machine works that's getting you the science. And I would like to point out that I have never once taken an engineering class, and I had to slog through all this stuff in order to understand it, wrote about it, wrote the manual for Curiosity, and now I can actually write a book about the science. And this is a moment that I want to give a huge thank you to the Flight Software Workshop, because without the Flight Software Workshop, there would be no text in a public forum that any member of the public could read that had anything to do with any of the electronic systems on Curiosity or any other NASA mission, because it's all behind, ITAR protections, and it's only when it gets out to conferences like this that people like me can actually read it. And so because of this workshop, I could write several chapters on this book. So thank you to the people who initiated this and have organized it for so many years. All right. So this was the last public talk. I put this slide in as a reminder. So in 2019, I left the Planetary Society to go freelance. I've been doing all kinds of cool stuff since then, but this is the last public talk I gave before the pandemic. And since then, I've been giving mostly Zoom talks, and so it's really fun to be back before a live audience. My last talk was really enjoyable because I got to speak in front of an IMAX screen. And that is the most incredible experience. I mean, the planets really were just about as big as they actually are, as far as I could tell. All right, so let's talk about Mars, which is what I said I was going to talk about in the first place. Before I talk about the renaissance in Mars exploration and science that has happened since 1997. I want to go back and talk very briefly about what came before it. So the first great age of Mars exploration culminated in the Viking missions, 2 orbiters, 2 landers. And they really saw Mars as a planet with atmosphere and and a whole geologic history, because they were able to stay for a long time, watch it change, watch it evolve. These are images that were shot by Viking 1 as it approached Mars. And I like to include this slide because it shows you just how beautiful the data are from the Viking mission. You don't usually see it like this, because usually most of the photos that you see are the versions that were processed in 1976, printed out, scanned, mimeographed, whatever, to put in print publications, and the data weren't touched since then, but the data are really this beautiful. And if you go back to the original data, which are all available in the planetary data system, the learning curve's a little steep, but for you guys, it's no problem, of course, and it's amazing how much beautiful stuff is buried in the treasure trove of the planetary data system that's just waiting to be processed with Photoshop, just modern processing technology. This is just layering the 3 red, green, and blue images on top of each other and making a color picture. It's gorgeous stuff. So this is what Viking saw on Mars. So you see a lot of impact craters, which tells you that the surface is very, very ancient. You see frost, so there is some kind of seasonal weather happening. There's the atmosphere freezes down to the ground. In the north, it tends to be water ice. In the south, it's carbon dioxide ice, and seasonally just water ice. But there is all these impact craters, which tells you that not a lot has happened on Mars since about 4 billion years ago. But in between the craters, Viking saw something really very cool, which are all of these valley networks. So if you look at the upper right of this image, you can see these kind of squiggly streams. They're branching, they're dendritic. So remember I showed you that channel on Venus? That channel had no branches at all. It was a single straight channel. It had a source and a sink, and that was it. These channels have many, many sources. So that means that either something like rainfall or maybe snowmelt or something was producing liquid all over a large area that was then collecting into tributaries and joining together to make these networks of valleys. And so there was a time on Mars that there was a liquid flowing on the surface, either under the air or under ice or under snow. But Viking couldn't really tell us anything more than that. It couldn't tell us, did the water last a long time, or was it just one freak event? Did it happen as a result of Mars's climate, or was there only water when maybe a big impact happened and briefly warmed the atmosphere and melted some stuff, and then it all went quiet again? The craters tell you that not a lot of change happened on Mars. So that period of wetness, it must have either been very brief or very intermittent, or else it would have obliterated all those craters completely. But you can look at the craters and see the floors are very flat. Craters should have a bowl shape, like all those lunar craters. They're bowl-shaped unless they're big enough to have central peaks. The fact that Mars's craters have flat floors tell you they've been filled in. But they could have been filled in by windblown sand or something. We don't really know whether those craters were filled in by sediments with water, or if it's just wind, or if it's lava. Lava also could make a level surface. You just don't know. So Viking left us with a lot more questions than we had answers. The landers went down to try to answer, their main question was, is there life on Mars? And the answer they came back with was, we don't know, unfortunately. I interviewed Matt Gollenbeck about this, who's a scientist at JPL, and he said, we swung for the fences and we struck out. And so they had these 4 experiments that were supposed to determine if there was life on Mars, and mostly they figured out, in retrospect, that when you add water to Martian soil, you make really, really oxidizing chemicals that just rip apart anything that would be organic material in the soil, even if it's organics that come from space, the stuff that's in like organic-bearing asteroids. There's naturally occurring organics that don't occur because of life. Even those don't survive it when you put water on today's Martian soil. It's very oxidizing, nasty stuff. So When the Viking program ended, it had left behind an immense trove of data, including all the data necessary to make this beautiful global color map, which they didn't manage to assemble, by the way, until the late 80s, maybe early 90s. And it was distributed then as the Mars Mosaic Image Data Record, or MDIM, and it was like split into 1 megabyte chunks and distributed on CD-ROM so that you could read it into your big computers that you had to buy the giant Macs, in order to assemble this thing. And this is still the color map of Mars that we use today. If you ever see a globe of Mars that has, Mars colors on it, it's from Viking. Viking is still the best global color data set that we have. And it probably will be for a long time. That little curl of white you're going to see again in the future, that's clouds over Hellas Basin. You can be sure that the people who made this map really did not want to have any clouds in there. But Hellas is very deep and it's always very cloudy, and that's the best they could do, unfortunately. So there's still that little bit of Mars that was covered by cloud down there. Okay, so after Viking was a dark era in Mars exploration. It was bad. It was bad for all of NASA. Nixon wanted to end the space program. The 1980s, there was almost nothing launched. Then when we started going back to Mars, we had a couple of really catastrophic failures, and things looked really bleak for a long time. But there were still a lot of Mars scientists around because of the Viking program. And so while they were waiting for some better news to come along, they formulated a plan for what are the questions we want to ask and get answered about Mars if we ever manage to get back. And so they came up with 4 Mars exploration goals. The first one is still the same one as Viking, is or was there life on Mars? And the reason that we ask that question is because Mars is made of the same materials that Earth was. It's basically the same distance from the sun. If life arises easily, as it seems to have done on Earth, we have evidence for life going back in the very oldest rocks that we can possibly explore, then it should also have arisen on Mars. And so we want to go see if the same conditions produce the same results. That's kind of a basic science idea, and that's why we're so determined to see if there ever was life on Mars. The second one is to characterize the climate of Mars, and a reason for that is actually, again, comes back to Earth, because Mars and similarly Venus are actually much simpler systems than Earth because they both lack large oceans of liquid water and life, both of which really confuse the chemistry, the global chemistry of the planets. And so studying the climate and weather on Mars and Venus are actually really helpful as sort of a simpler case for our climate and weather models. And then we can bring those models back to Earth and see if they work for Earth. And that kind of process has really improved weather and climate prediction for Earth over the years. Characterize the geology of Mars. This is more about understanding how a terrestrial planet works, again, without life, because life makes dramatic changes in how geology works. Just, the power of trees binding soil and organic critters eating up rocks can really change the geology on Earth. So Mars is a place that has geology without life. And then prepare for the human exploration of Mars. Why? Because some people seem to want to. I personally don't care, but some people seem to really want to go there. And so in order to make that happen, you have to make some preparations for it. Is the chemistry of the soil going to eat you? Is the dust going to grind all of your instruments and your rovers to a halt? Are there unforeseen life effects? Just how bad is the radiation? All of these kinds of questions you have to answer before you can send humans there for long-term exploration. So all of this culminated in what's been known as the follow the water strategy that was announced in 2000. Even though it was announced then, it really is just a kind of mantra or a slogan for this set of 4 goals that Mars scientists came up with in that doldrums between Viking and the next missions. So like I said, Pathfinder in 1997 really was not a scientific mission, an engineering mission. It was meant to test out a bunch of technologies for future exploration. The rover was actually kind of a late add-on. And just like the helicopter on Perseverance, to fast forward, it was not welcomed by a lot of the science and engineering team because it added so much complexity, but it did add also not only capability, it tested capability that we used in the future, but it just became the public face of the mission. And it inspired people like me and a lot of other people to be really interested and excited about space exploration, and was kind of an impetus to public interest in planetary exploration for the next couple of decades. So yeah, there's I love little donuts it makes in the soil. It's really cute. Okay, so Mars Global Surveyor arrived at the same time, and Mars Global Surveyor produced this topographic map of Mars. So we didn't have a global topographic map of Mars before MOLA. And I don't think very many people appreciate just how important this data set is. But if you've ever taken a geology class or watched how exploration happens, you know you start with a topo map, right? If you go hiking, you start with a topo map if you're headed into the wilderness. The shape of the landscape tells you a lot about the history of the landscape, and it also gives you the base map on which you put all of your other information. The MOLA data set allowed us to register all the other data sets to each other, which multiplies the value of every data set. So looking at this global map, which became available, I think, around 2000, so it was several years after Mars Global Surveyor survived, y'all can see a couple of very profound things about Mars that we didn't really know until we saw the MOLA map. The main thing is that Mars goes downhill from south to north, like just in general. You can look at that. It's red at the bottom and blue in the top. Which is weird if you think about it. Like, wouldn't the planet make the center not go downhill? Like, shouldn't it? No, it's actually because of the way that the crust is built, it balances out so that the topography at the very top surface is low in the north and high in the south. And that's important for several reasons. It's important for climate reasons. It's also important for liquid flow, both on the surface and underground. So any liquid that lands on any place on Mars generally flows from south to north. And you can actually see that if you look at all the outflow channels and all the other channels. There are channels that are big enough to be seen from this far away. You can see they're labeled right up there above the Valles Marineris. They all flow from south to north. And so that tells you some things about where to look for evidence for water. And if you follow the water, you follow it to where there may have been places that life could once have existed and possibly even does today. Also, you can see Hellas Basin really is the deepest thing around. It is very, very deep. It's the last big impact that happened on Mars. And you can see it's all high around it. That's all the ejecta that landed around it. So one reason those things are able to be so high is because it's pulverized crust. It's very porous. We think that there's actually a lot of airspace. It's very blocky, and it's not dense rock. It's just crumbled up crust from that late huge impact. The other thing you can see is that there really is a dichotomy in elevation between what are called the southern highlands and the northern lowlands. The southern highlands are more ancient. You can see they're heavily impacted craters. The northern lowlands have very flat floors. It's very tempting to think that Mars had a northern global ocean at some point with all those channels emptying into it. And they've made it even more tempting to think that way by coloring it blue. They maybe should not have done that because it really makes you think that's an ocean. It could have been, but we don't know for sure. There's a lot of evidence on either side. It may never have been entirely filled or all filled at once, or we just don't know. It's flat because of volcanoes. It's flat because there's a lot of lava that got extruded into that area. It may have had an ocean, we don't know. Some people argue very stridently that it did, and anybody who doesn't take criticism should not be listened to. Okay, so Mars Global Surveyor had other instruments, and one of them was a thermal emission spectrometer, or TESS. And so in thermal wavelengths, which are like 10, 20 microns, you can get at the mineral composition of the soil, of the surface. And this is a map that TESS made of a specific mineral called high calcium pyroxene. You don't need to know what pyroxene is. All you need to know is that this is a mineral that shows up in fresh volcanic rock that has not been broken down by water, and also that is exposed at the surface so that you can see it. And so this map is kind of a good map to be a guide for where is there bedrock on Mars? Where is there rock that hasn't been altered, that hasn't been blasted by radiation for billions of years, that hasn't been covered with dust? This is a sign for places that you might go to explore to look for bedrock and maybe answer some of your questions about the history of Mars. Tess also saw one other really interesting mineral, and that mineral is called hematite. You might know hematite as a metallic dark gray mineral. It often shows up in like semi-precious stones, in the tumbled rock shops and stuff like that. It forms in the presence, there's really no way to make it other than with water. And there's that one little beacon of hematite up there on Mars. It's located right at the prime meridian and the equator. It's just like there's a big X on the spot. Go there and look for ancient water on Mars. So that's what we did. And we sent a rover called Opportunity there in 2004. And this was the very first photo returned from Mars by Opportunity. And it was taken even before the camera mast had been raised. So we're looking down the mast like this before the mast pops up. And we are looking directly at bedrock. And I cannot tell you how excited the scientists were when they saw that bedrock. They called it the Great Wall. They were so excited to see bedrock in place, because bedrock in place, it's there, it's where it formed. And that tells you something, the fact that it's in situ, the fact that it's there, it's like an archaeologist who wants to see things as they come out of the dig, right? Instead of just, having some random artifact that they're handed like without its provenance. We know that rock has been there since it formed. And so it can tell us about what was happening in the past on Mars in this spot when it formed. And so they were very, very excited to see this. Turns out it's not a great wall. It's about that tall. But the scientists were really excited. So Opportunity got closer. And when Opportunity got real close, you could see that the rock was rather light colored for Mars rock. All the soil around it is basaltic sand. It is very, very dark. It's brighter here because we've increased the contrast so you can see things better, but that sand is really dark. And then buried in the rock, you can see these little spherules. They're bluer or grayer than the surrounding rock material, and it turns out that's where all the hematite is. And the hematite is in concretions. Concretions form underground after a rock has already formed, when groundwater is flowing through the rock and moving chemicals around, and then the chemical gets saturated and it starts to precipitate out, and it makes these little round spherules. And they call them blueberries because they look like blueberries in a muffin. And that's what they're known to this day as. Those are the blueberries on Mars. Opportunity went on to explore much better exposures of ancient bedrock. And you can see how beautifully layered this rock is in the wall of a crater. They were actually driving Opportunity on a slope where it would slide downhill about half as much as it slid forward for every drive. This was fairly late in the mission. They were taking some risks with driving the rover. It was like white knuckle driving for the rover drivers, but it was pretty awesome. By the way, there wasn't a drone or anything to take a photo. That's a simulated view of Opportunity, just put in the image so that you can see the scale of what we're looking at. And so you can see all these layered rocks. The layered rocks are all made of a material called, it's a sulfate mineral, mostly calcium sulfate. And those kinds of minerals form on Earth in places where you have a really, really briny, evaporating water in a very dry desert. So if any of you have ever been to Death Valley and you've seen the sort of the crystalline rock that forms in the kind of the very deep valleys where water goes in, it doesn't come out, it leaves behind its minerals, and the water can be very, very acid. The water where this stuff formed would have been like battery acid. It would have been really nasty. Not a great place for life to originate, no, but there are extremophiles that survive in these kinds of environments. So if life ever arose on Mars, this kind of environment wouldn't have prevented it from continuing, but it's not exactly the nice kind of place that you would imagine chemistry happily happening and life being able to just spontaneously emerge from accidental chemistry. But it is water on Mars, and so that is what we were looking for. It just wasn't as nice as the water on Earth is. So there were two rovers. The other one was Spirit. It was sent to a place called Gusev Crater, which you can see from space. It's the big flat one toward the right of the screen. It clearly has a valley, a channel emptying into it. There clearly, no question, was a lake in this crater at some point. But if you look at the top of the image, slightly off screen, you can see there is something that is making a fan kind of out into the landscape to the north of the crater. That's volcanic, and that turned out to have been important because when Spirit landed, this is what Spirit saw, a flat, it looks just like Viking, just like Pathfinder, flat plain littered with boulders that were thrown there by impacts, all of it basalt. They drove Spirit to the rim of a crater hoping that they would find bedrock just like Opportunity did, and there's nothing there. It is just, there may be bedrock under there, but it's all lava. They called it a basalt prison because it was not the lake bed sediments that they were looking for. So out in the distance, they saw what they called the Columbia Hills after the astronauts who'd lost their lives in the disaster just recently. And they said, well, Spirit's prime mission is almost over. We don't know how long the rover will last, but let's try making it for the hills and see if these hills, which appeared to poke up through the lava at the bottom of the crater, let's see if those hills contain more ancient rock that might have some watery story to tell us. And they reached the base of the hills on Sol 170, 80 sols after their warranty had expired, and they found this rock called Pot of Gold. And you can see from its shadow just how weirdly shaped that rock is. So it clearly also has some kind of concretion-y something that's more resistant to erosion than other parts of it, and that's because, just like the rocks at Opportunity's landing site, it had once been saturated with water. Again, very sulfate-rich water, very acidic water. So we have two rovers on literally opposite sides of Mars. One of them landed at about longitude 0, one of them landed at about longitude 180, both telling us about an age of Mars where there was plenty of water around. There was water for these rocks to be deposited in, and there was water later that came in order to alter the rocks and make these concretions and stuff. So there's water, but it wasn't the really nice environments that Earth has, not the kind of thing you imagine where life arises. But they kept searching. Spirit, when it's later on in its mission, one of its wheels froze and it tended to drag this wheel behind it, and it accidentally unearthed this incredibly light-colored soil at a spot called Gertrude Wise. And this soil was almost pure silica, opal silica, and that forms near fumaroles, places where, imagine Yellowstone, places where there's hot mineral water coming up from volcanic warmed rocks from underneath. And there was definitely a fumarole type environment. And you know, anybody who's ever been to Yellowstone or any other hot springs knows that there's funky algae and other kinds of stuff that live in those springs. Again, not lovely lake water at neutral pH, it's acid stuff, but I mean, that would be a persistently warm liquid environment for a real long time. Might have been a nice place to live if you're a certain kind of extremophile. We don't know. All right, so the Mars exploration rovers established that there were places on Mars that were saturated with liquid water at some point. So that was a good start. It still wasn't the environments we wanted to see. Mars Express arrived at the same year, actually, that the Mars exploration rovers did. This was a European Space Agency mission, and it carried its own kind of spectrometer called Omega. Omega was different from TESS in that it could see more into shorter wavelengths, near infrared wavelengths, and those are very important for a reason I'll explain in a moment. I just wanted to show you that their pyroxene map matches the TESS map. It just has a bit more detail on it because Omega is capable of seeing at higher resolution than TESS was. TESS had really big pixels, Omega much smaller, and so consequently it took them a much longer time to build up a global data set. With their near-infrared data, they could see really tiny exposures of rock that had minerals in it that were hydrated. And hopefully you guys know your roots well enough to know that hydrated means water. So these are minerals that it's not that the rocks have water in them, it's that the minerals have OH little additions to their crystal structure. So you have minerals like clay that form when you take a volcanic mineral like pyroxene and you attack it with water and you bust apart its really interlocked, very strong crystal structure, and you make it into all of these thinly layered platy minerals that are called clays, and those plates are held together by the water bonds, the OH bonds, and that means that these minerals are just stuffed full of water. And so they're mapped on this map with these little tiny green dots, which are in every case larger than the exposure of material that Omega actually saw, but they just had to make the dots big enough so you could see them. They're exposed in only very limited places because it turns out they are the most ancient rocks that we can see exposed as bedrock on Mars. They are in places that are beneath, lower than the highly acid sulfate-bearing rocks that Spirit and Opportunity explored. So we said, aha, if we're going to send another mission to the surface of Mars, we need to send one that can get to that specific kind of bedrock, the kind of bedrock that is older, lower stratigraphically than the sulfate rock, because that is where those clay minerals, they form in environments that are not so acidic. They form in environments where it's just wet, just plain wet. One of those spots is in one of the deepest holes on Mars. It's not as deep as Hellas, but it's pretty dang deep. And that spot is named Gale Crater, which may be familiar to some of you. I'll be coming back to Gale Crater. All right, so Mars Reconnaissance Orbiter, NASA mission was sent in 2006, had this amazing camera with a resolution on the surface of 25 centimeters per pixel. Which is just, I mean, just think of that, that's your foot, okay? It didn't cover all of Mars at that resolution, it couldn't, but it just little strips, you know, covering some small percentage of the planet, but it picked out places like the ones that Omega had seen, where there were these really ancient rocks that had interesting minerals exposed in them. And so this is a photo of the interior of Gusev Crater, and there's a little friend sitting down there. That's Curiosity, seen from space by Mars Reconnaissance Orbiter high-rise camera right after Curiosity landed. You can see the fan is from the descent rockets as Curiosity landed. And then over here is the very first place that Curiosity went to explore. So when it landed, the landscape, again, looks kind of familiar, you know, flat, nothing interesting there, just rocks just on the surface. There is this really cool mountain in the distance, but then there's a whole bunch of black sand dunes that are in between the rover and the mountain. So rather than head straight for the mountain, which is where they really wanted to go, they first took a little detour and went to an area that had obvious exposures of these layered rocks. They passed this pretty early on. To me, this looked totally like broken concrete. And you know, on the way to LAX, there's all these trees that like have completely just upended the concrete. You can see all the little the gravel that they put in concrete in order to fill it up. You can see the little rounded bits of gravel falling out of this. And this is a rock that is made of many different sizes of other rocks. Some of the rocks that are buried in it are rounded, okay? Where do you get rounded cobbles? In streams. And so we figured out from Curiosity that just within very few days of landing, that there had been surface streams running across the ground here, somewhere between ankle and hip deep, that had moved these rocks and left behind these deposits of conglomerate rock. So within very early days, we were like, aha, we're in the right place. This is just water running on the surface. This is not a volcanic hot spring. This is not a incredibly acid evaporating lake. This is just water flowing from uphill to downhill, and it's just water. So this environment is also not great for originating life. It's too high energy. Everything gets all crushed up by the rolling action of the water, but the water is going to run downhill to some place where it's going to pool, and that's what we're looking for. So Curiosity, after exploring this area for a little while, you can just see it's a geologist's paradise. You can see all these layered rocks just waiting to be explored. This is that first area that Curiosity explored. It really looks like a shoreline. It's not. It's just flat-lying rocks that were then eroded into by the wind, and so it made this kind of false appearance of a lakeshore. The whole thing was actually lake at some point. And it was all filled up and deposited continuous flat layers. And they were able to start like doing real, honest to God, field geology with Curiosity. It was just stunning. They started naming the types of materials. They were able to take this microscopic imager, go really up close to the rocks and see the sand and granules that they are made of. These things are very tiny. And they actually brought a drill with them, which is just so cool, and learned the fundamental truth that Mars is red on the outside and gray on the inside. which sounds like a joke, but it's actually very important. The red outside is that highly oxidizing, nasty chemistry that destroys organic materials. The gray interior is reducing. That means that the iron is not oxidized. The iron is in a reduced state, and that is what you need to preserve organic materials. So not only are the materials, they could have formed in this type of chemistry when the sediment was being laid down, but they could also have survived to the present day to be detected by scientific instruments because they have not been in an oxidizing environment. They've been in a reducing environment, so they could have been preserved. And so Curiosity has gone on to find organics in rocks. So we have not found evidence for life, but we have definitely found evidence that Mars had environments that could have supported life in the past. And the next several slides are just me showing pretty pictures from Mars. This is just Curiosity exploring glorious bedrock, finding that Mars is different colors on the inside in some places, even though it's the same red all over on top. These are what you call cross-bedded sandstones. So you can see how there's very, very thin layers, and then some of them truncate up against each other. That happens when you have water flowing and moving sand, and it forms, like if you ever watched river or and these are active sand dunes. They are made of basalt sand, and they are what we have to credit for the beautiful exposures of bedrock in Gusev Crater, because they have been driving off all of the dust. They've been scouring the surface, eroding into the bedrock, and exposing relatively fresh rock for Curiosity to look at. Fresh, maybe a few million years old, maybe a few million years exposed instead of billions of years exposed, which means, again, you have the chance to find those organic materials that are so fragile but actually have been preserved over billions of years in these rocks. And so this is just a snapshot from a ridge that Curiosity explored a couple years ago. And this ridge is really super cool because the ridge was made in one kind of rock laid down in a lake, and then it was altered by groundwater not once, but twice, 2 different episodes of different chemistry of water flowing through it and hardening it into this really resistant rock that actually Curiosity had a terrible time drilling into. They had to try like 6 different times around the top of this ridge in order to drill into it and get a sample. And Curiosity has now gone up the mountain and has explored from the clay era, the oldest era of Mars, where it was warm enough, clement enough, wet enough to have that nice neutral pH chemistry that we could imagine life forming in. Curiosity has now climbed up into rocks that formed during the sulfate era later on, when in the kinds of rocks that Spirit and Opportunity explored. So Curiosity really marked the success of the follow the water strategy. We have definitely characterized the current climate of Mars and are learning more about the past climate. We've made great strides in characterizing the geology of Mars. We still don't know if life ever arose on Mars. And we've done some work toward preparing for human exploration. So that one red X there, the thing that we still don't know about, is still the goal for Mars exploration. And that's what led to what's now the beginning of the next phase of Mars exploration, from following the water, determining the ancient climate of Mars, to the search for life. And so that's what Perseverance was sent to Mars, not to search for life, but to drill for rock samples that could be analyzed later, returned to Earth, and analyzed with the full capability of Earth-based laboratories to try to understand what the chemistry was, and if we're real lucky, find evidence for past life on Mars. Perseverance is not as capable scientifically as Curiosity is. Perseverance does not have the onboard laboratory capability that Curiosity had to analyze the science. It depends on returning samples. And so ESA had plans for an ExoMars rover that has been delayed about 12 times since it was first proposed. Still don't know if it's ever going to launch. I hope it does. I hope it lands safely, but God only knows if it will. And what we really need is to get the samples back to Earth, which is why the last couple of reports that have come out from NASA evaluating the readiness for Mars sample return have not been very favorable. And so that's really the next step in this goal to understand ancient Mars as as the same kind of laboratory that ancient Earth was to prepare to be a place where life could have been born, where life could have originated. And it's going to take international cooperation. It's going to take a lot of really creative engineering. There's been a lot of great ideas proposed, but they haven't moved forward yet. It's going to take a lot of money, and that's going to take public advocacy for it, which means not only that y'all all ought to be, talking to your Congress people about I support space exploration, but you should do as much public education as you can around exploring space or any other goal that you might find important, planetary debris removal, anything else. Make sure that you use the fantastic educations you all have and the knowledge that you have to inspire and educate the public about what we need to do to further space exploration, further exploration of the Earth. So thank you very much for your time. I'd be happy to answer any questions, and please buy my book.
First off, thank you for coming here. I really enjoyed your blog entries while you were at the Planetary Society. Let's see. As someone who's been an observer of the history of Mars exploration and also knows about the geology of it, where do you think we should go next?
Personally, I think we should go to Uranus or Neptune rather than back to Mars next. But that's just me. So if the answer is where should we go on Mars next? So Perseverance is exploring an ancient delta. That's a real good question. We've been inside several craters. I want to go to a place that's not inside a crater. I want to go inside a canyon. I want to go to see some different kind of landscape. But that's just the tourist in me. I actually don't know scientifically what's the best. Really, I'm in it for the tourism. It's fun to see all these new places. Every corner you drive around gets you a new kind of landscape, a new kind of scientific puzzle to solve, and that's what's fun.
Yeah, we have a question online. In the Venus image, how do you know which end of the canal is the sink and which one is the source, since there are no branches?
That's an excellent question. There are almost no branches. However, there are some places where the channel does something called anastomosing, and that's where a channel that is going across a fairly flat landscape kind of breaks up and kind of comes back together. And so from the anastomosing channels, you can infer a flow direction. And also there is a general downhill from one place to another place. If you graph the topography, there is a definite downhill trend along its length, but it does have some funny lumps and bumps in the middle. And that led me to conclude that the ridges and mountains that we'd seen on this Venus landscape, they had existed, some expression of them had existed before the channel formed, but they were still rising. There were still active tectonics happening. So that's not just volcanism, lava erupting, but tectonics are when forces make the crust move, bend, break, open, or crush together. And so that Venus was changing in the time after that formed. And the reason that was important is because there's a big debate in Venus science about whether Venus is currently active or whether it had about 500 million years ago, which is based on how many craters there are, it had this sudden paroxysm of global volcanism and all these eruptions and everything happened and then it quieted again. And so the thing that I was looking at was a way of trying to piece, had things changed much or not since the volcanism happened? You don't have to ask about Mars either. Ask the other space questions. It's fine. There's one over here.
Sorry, where? Oh, okay. How do you think that we or exploration advocates should think about balancing the needs for Mars sample return versus the needs of other science missions that could be, for lack of a better term, starved of resources because of the amount of resources it takes to do Mars sample return?
So I think that actually that's not your job. Your job is to advocate for the things you want, and also to advocate in general for more of everything. And then it's NASA's job and Congress's job to decide what the top priorities are. Or, you know, they get committees together, like the National Academy of Sciences, and the decadal survey process gets a lot of input from a lot of scientists, a huge community, and they set priorities. And so, but you individually, just go for the things you like. I want 2 orbiters sent to Uranus and Neptune that are identical. I want them there when they are in near equinox, so we can see the north and south poles of all the moons, which means they need to be there in the 2040s. That's all I want. just a small ask, small request. Only $5 or $8 billion, just chump change.
Yeah, we have a question online, then we can go in person. Okay, the next one is, how could you determine if tiny living organisms like bacteria ever lived in Mars? Could you explain this process, please?
So looking for bacteria or other microorganisms, which is the smart thing to do, by the way, because after all, life existed on Earth for 3 billion years before it became multicellular. As far as we can tell, life arose on Earth almost immediately, but it was not multicellular until about 500, 600 million years ago. So you want to look for very, very microscopic life. One thing to do is to look for obvious fossils, and actually it's easier to do that in some ways on Mars. And the reason for that is because Earth has been very geologically active for all of the last 4 billion years. So those most ancient rocks that we can find evidence for life in, they are horribly altered. They have been buried deeply. They have been heated to very high temperatures. They have been squished. They have been all different kinds of groundwater have flowed through them, have altered their chemistry. It's horrible to have to try to look in them for any evidence of fossils. Whereas all these rocks exposed at the surface of Mars, the things that Curiosity is looking at were formed probably around 3.8 billion years ago, were gently buried. They were buried enough to compact them into rock so that they're now resistant, now that they're being eroded again, but they were not buried to depths where they got high temperature. They were not crushed in tectonics. They've had plenty of groundwater flowing through them, but they're generally speaking not a lot different from what they were when they first formed. And so it would be a lot easier to see evidence for the actual physical things in the rocks, using a microscope on Mars than it is on Earth. But you don't always see the actual fossils. Sometimes you're just looking for trace evidence. So that's chemical evidence, things like chirality of molecules. You know, when life makes proteins, at least when Earth life makes proteins, proteins have 2 different enantiomer. They have 2 different forms. They're the same chemically, but they're mirror images of each other. Life prefers one of the 2 mirror images. And so, because that's just the way it gets assembled in our cells. And so if you can find ancient organic material preserved in rocks and determine that there is a lot more of one mirror version of a chemical than there is of another version of a chemical, that tells you that there is something other than a natural process making that material. So that's one of the really big ones. Another one is isotope fractionation that would happen through life-like chemical reactions. There's a number of different ways involving organic chemistry. And so that's one reason why we really want to get samples back to Earth, because you just can't do that kind of organic chemistry in a microwave-sized box inside a moving rover that you have to launch on a wildly shaking, terribly accelerated launch vehicle and then land by whatever process on Mars. You just can't do it. And the development of the instruments that Curiosity has did enable mobile exploration with these kinds of laboratory instruments back on Earth. It's great. There's a couple of different instruments, including the neutron generator and receiver that's in Curiosity's butt. That thing did not exist as anything smaller than a truck before it was developed for Curiosity, and now it's used in geological surveys all the time. So there's miniaturization can happen, but for really good laboratory work, you have to be able to see just incredibly infinitesimal amounts of an organic chemical, and that requires extremely sensitive labs on Earth.
Great talk. When when Sojourner popped out and all of a sudden we had mobility, it felt like a step function for what you're able to do for exploration. When Ingenuity started flying, to me, it felt like another step function. I'm interested from a science perspective. It also felt the same. And do you feel like that there is another step function after that?
That's an interesting question. I think, yeah, it's hard to know yet if it's more gimmick or if it's more something that's really going to be awesome. I think that it can be awesome. I think there are two ways that Mars exploration could change really dramatically in the near future. One of them is a concept that has been around for a really long time, which is send lots of little exploring machines. Now, in order to do that, the advantage is obvious. You have a lot of things. You can afford to lose some of them. They're all taking the same kind of data in wildly different places. And so it's really great to have lots of little machines, but they all can't communicate direct to Earth. So there needs to be some kind of infrastructure in place for communicating their data back to Earth. And so that's, I think, and that would be one really interesting enabling mission, would be if somebody just sent a spacecraft whose sole function was communications, just a ComSat for Mars, that could then enable many, many, many little tiny missions to try and fail and then succeed. And then we'd have, I think that would usher in a renaissance for Mars exploration. The other capability that's a little further in the future, but that I think is something that could be really thrilling, is involving humans more directly, but not by landing them on the surface, because just getting down there is, the technology to require it is really difficult to overcome. In the present, obviously, at some point in the future, we'll be able to do it. But in the present, there are so many problems to solve. Getting people down there, helping them survive, not die, get back. It's all extraordinarily difficult. I think an earlier step would involve having humans in orbit, teleoperating machines the way we do here on Earth, teleoperating machines in dangerous environments, because that way you get the human brain, you get the instant reactions, you get the dexterity, you get the choices that we can make about questions and answers, and you get robotic capability to survive the extreme environment and not need to be fed, and all of those other problems. And so I think that coupling, people are often asked, do you like human better or robot better? And you use whichever one is suited to the task, and they can work together. And I think that is really the path forward for scientific exploration, because you really do need to get a human brain in the loop, more in the loop than it is now. But you also need to not have to solve all of the problems that are inherent to surviving in such an extreme environment. So I'm hoping that our investments in human exploration in the future will be less like, cowboys on the prairie, with this kind of, imagination, romanticization of like the lone explorer going off into the black and filling in the map. Rather, I think there's a partnership between lots of humans and the robots that are going to be, exploring the environments for us, with us, as our avatars. There's a really interesting book written by a sociologist whose name is Janet Vertesi. She calls it, Seeing Through the Eyes of the Rover. She was embedded in the Mars Exploration Rover mission for a while, also in the Cassini mission for a while. And she wrote this book about the way that the scientists and engineers on the rover teams envisioned their exploration of Mars with the rover. She noticed something very profound early on in the mission, which is the pronoun that they used for the rover. Some people use it, some people use she, but everybody at some point uses the pronoun we. So we drove 100 meters today. We put the rat on the rock and grounded. We investigated this, that, and the other thing. So the rover really, to them, embodied all of these, the whole team working on Mars. And even when they were imagining how they were going to plan for the rover motions, you see me doing these arm motions, they put their arms down. They imagine, okay, I need to look over here so that I can have it in place for, and so in a very real way, those team members were already imagining themselves as that rover exploring on Mars, and I think it's just going to get more and more like that in the future. Yeah, back there.
Thank you so much for the talk. I was wondering, do you have a recommendation for a good first step for an engineer like me to get involved in public outreach?
Yeah, I would say through the Planetary Society is one. A second one is through JPL's Solar System Ambassador Program, which is really excellent. They give training materials. They have periodic talks by scientists to all the solar system ambassadors. And they do really great work reaching out to all kinds of public groups and giving you the support you need, the training you need to be able to speak knowledgeably and answer their questions. Plus, they send you free stuff that you can hand out. So it's great. Unfortunately, it's only for American citizens. And I think that one amazing thing would be if there were some organization, some research organization, some country, whatever, who would form a partnership that would make use of the public solar system ambassador materials but enable access for educators in other countries. That would be really, really valuable.
Thank you so much.
We can take a question online. Given the opportunity, would you take a trip to Mars?
I like that question. Given the opportunity, would I take the trip to Mars? Absolutely not. I am very comfortable exploring space from the comfort of my own office in my pajamas, where I can eat whatever I want and not risk death at all moments from anything. Plus, on top of that, Mars, Mars is cool, but it's not all that. There's so many other cool places to explore, and most of them we can never even imagine sending people to anytime in the near future. Not just Uranus and Neptune, which are current, they haven't been explored enough. I want to go back there. But moons of Jupiter, Venus, surface of Mercury, there's so many places to go. Let's just send all the robots and I can drink my coffee and see them on my computer. There's a question back there. Oh, yeah, go ahead.
Actually, that leads into my question. Everything you mentioned right there was planetary exploration. For a while, asteroid exploration, asteroid mining was a hot topic. Do you see any scientific value to that, or is it just a gimmicky, shiny object?
Asteroid mining is something that it'll probably happen at some point in the future. It's more of an engineering problem than a scientific problem. I am very interested in how asteroids are built. I am very interested in understanding them well enough that we can deflect or move one should we ever discover one that is on an impact course with Earth. That's actually one of the topics of my next article for Sky and Telescope, which is about the DART and Hera missions. That we're running an experiment to see if we could move an asteroid from its path. And so I think it's interesting to study asteroids. I really don't care about bringing those resources back to Earth. I think that maybe we should make better use of what we have down here when it comes to, But on the other hand, near-Earth asteroids are near, and they are easy targets, relatively speaking, for exploration by very small spacecraft. So I am interested in lots of people sending as many spacecraft as they can to go see them and see how weird every one of them is.
There are a few more questions online. Unfortunately, we are running out of time, and you can.
But I'll answer them on Slack. I'll go into Slack and I can answer.
That would be great.
Yeah.
Thank you so much, Emily.
Thank you for having me.